Great. I gotta say that I got it. There we go. Okay, cool. All right, I'll go ahead and get started. Thanks for having me. Happy to be here. So I'll be talking about tunings and new physics searches in neutrino experiments. I'm a grad student at Chicago and also kind of at Fermi Lab. And this is a project that I've been working on with Shirley Lee and Pedro Machado at Fermi Lab. Okay, so this is a relatively experiment heavy talk. There's a good amount of experimental details. So most of the, well, about half the talk is actually going to be kind of in the setup of the problem that we're investigating. So first, I'm just going to go through an introduction and explain why we need to worry about neutrino cross-sections in the first place, because neutrino-nucleus cross-sections are actually quite difficult to calculate. Then I'll go into a little bit of the current status of neutrino generators. So neutrino generators are the way that experiments typically generate their simulated spectra so that they can compare with their data. And so I'll kind of look at an illustration of how well those generators can actually do at the moment. And then I'll talk about near-detector tuning. So we need to worry about cross-sections, which I'll set up in the first two parts. And near-detector tuning is the way that experiments try to adapt their generators to accurately predict the data that they see. And this is a process that can be kind of confusing, particularly for theorists, so we'll spend some time on that. And then we'll finally get to the new physics part. So we'll look at the interplay between tuning and new physics searches. And we're going to focus specifically on two models. The first is an EV scale sterile neutrino. And then the second is looking at neutrinophilic scalars. And we choose these two models because they have two different signatures that we hope can kind of be representative of a number of different new physics searches. And then finally, I'll just wrap up with conclusions. Okay, all right. So before we dive into all the nitty-gritty experimental details, let's just remind ourselves of the basics of neutrino oscillations. So of course, in the standard model, we have three flavors, and that's a bit more complicated of a case. So we'll start with just a two-flavor setup because I think that gives us more of a conceptual understanding of what's happening. So the basic idea is that you have a rotation or a mixing between your flavor eigenstates and your mass eigenstates for neutrinos. So these new A and new B, also sorry, I have naturally shaky hands, so if this gives you a headache, I apologize. I'll try to two-hand it. You have your flavor eigenstates that you actually produce in interactions, new A and new B. And then on the right over here, we have the mass eigenstates, which are actually the propagating eigenstates. And so when they propagate, they pick up different phases if they have different masses. And this is basically why neutrino oscillations show that neutrinos have mass, because in order to oscillate, they have to have different masses. And here we have our rotation matrix. So this angle theta is basically your mixing angle, and it tells you how much your two flavors are actually mixed. So what this results in is this oscillation probability over here on the left. So what we've written down here is the probability that you start with some neutrino of flavor A, and it oscillates after some distance traveled into flavor B. So you have two parts. The first is your sort of amplitude of your oscillation. And that depends on your mixing angle. So you can see, since it's sine squared of 2 theta, if you have, say, mixing angle of 45 degrees, so basically you have your flavor eigenstates are an even mixture of the two mass eigenstates, then you'll get maximal oscillations. So that's the amplitude. And then you have the actual oscillation term, and it depends basically on three pieces. The first is that mass squared splitting. And again, you can see that if this is 0, you're not going to end up with any oscillations. Then you have the distance traveled by your neutrino and then divided by the energy. So there's really, I think this is where it goes, yeah. There's really kind of two pieces when you're thinking experimentally about how to look at these oscillations. So you can think of it two ways. First of all, you could say, okay, I have a given mass squared splitting. That determines the ratio at which of L over E at which you'll actually be sensitive to oscillations. Or you could say I have a given L over E, and I'll be sensitive to some mass squared splittings, but not others. So this is kind of relevant for the standard model because in the standard model, the mass splittings are actually about 2 orders of magnitude different, or I think it's like a factor of 30 actually. So you have one mass splitting at about 10 to the minus 3 v squared, and then another at about 10 to the minus 5. So they become relevant at different ratios of L over E. And this means that you can sort of design your experiment to look at different oscillation parameters. Okay, so this is the sort of basic of the standard model setup. So we have 3 flavors of neutrinos. And so if you want to parameterize your mixing matrix, you can parameterize it basically as a product of 3 2-flavor mixing matrices. And what you end up with is an expression that's rather more complicated than the one that we wrote down in the previous slide. But again, you can design your experiment in a way that you're sensitive to certain mixing parameters more than others. So you can at least a little bit try to simplify the problem that you're looking at. Okay, so in this talk, we're going to be focusing on accelerator neutrino experiments. So this is a basic sketch of how it works. I realize to me, this diagram is ever present at Fermilab. It's about everywhere on every single floor because this is Dune. But just this may not be as familiar, I'm realizing, but this is the diagram basically of Dune. And what you do for an accelerator neutrino experiment is you're looking to measure typically standard model oscillation parameters. And to do this, they use a 2-detector setup. So they have a near detector, which is generally denoted by ND, and then a far detector, which is FD. And basically what happens, as Kevin was kind of stealing part of my talk at the journal club this afternoon, you have a proton beam that you generate and it hits a target. This creates some pions and then those decay into your neutrino beam. So typically what you do is you have a very large far detector at a certain distance such that you're maximizing your sensitivity to the oscillation parameters you're interested in. For NOVA, which is the experiment we'll be focusing on, this is about 810 kilometers away from your beam source. And then you have a near detector, which is typically placed very close to the beam source, and we'll get into why in a minute. And you try to make that more or less a smaller version of your far detector as best you can. You want it to be very similar. And what you do with this near detector is you look at the data that you see there, and you use this to reduce your uncertainties in the flux and in the interaction cross sections for neutrino-nucleus interactions. So this is the basic setup. We can make this a little bit more precise with some math. So here what we have is sort of what I would call the setup that you would get in an idealized perfect experiment where the world worked exactly as you wanted it to when you're building an experiment. So what we have is we're looking at a probability of oscillations for flavor alpha, flavor beta, whatever they might be. And you basically just take the flux at the far detector for your flavor beta and divide by the flux that you started with at the near detector with flavor alpha. And then this is the flux. So we can rewrite this in terms of slightly more experimental quantities in terms of the event rate that you see. And you have to divide out the cross section of your neutrinos with your nuclei, because not every neutrino is going to interact with your detector and you have to account for the cross sections. So again, you just do the same thing for the far detector and the near detector here. And at first glance, if you look at this expression, it appears that the cross section more or less cancels out in this ratio. This is what we call near-Defart cancellation. You might wonder about if you have a different flavor, alpha not equal to beta. That's a little bit of a complicated story, but hypothetically, you can account for the differences in the flavors. And if you do that, you can go ahead and cancel out these cross sections. So first you say, great, I don't have to worry about cross sections as long as I have 2 detectors. But unfortunately, that's of course not the case, or else this talk wouldn't exist. So the problem is that you don't actually measure the true neutrino energy. What you measure instead is the energy of the final states, and you reconstruct the neutrino energy from that. So here I've written down a very basic expression. We're going to be using NOVA. So again, these are going to be muon neutrinos that we're looking at for our analysis. So basically what you do is you reconstruct it from the energy of the muon that you measure. And for NOVA, they can measure this to about a 3% resolution. And then you have your hadronic system, which is somewhat messier. And for that, NOVA thinks that they can have about a 30% reconstructed resolution. Part of the problem is, for example, you have neutrons, which aren't actually really visible for the NOVA experiment, and they have to sort of statistically account for how much energy might be in neutrons that they can't actually see. And so it's rather difficult to successfully reconstruct this. So basically, what happens is that your oscillation probability that you're trying to extract from your experiment depends on the true neutrino energy. But what you're actually seeing is the reconstructed neutrino energy. And so basically what you have is sort of like a smeared distribution relative to the true neutrino energy spectrum. So you're trying to extract oscillation probabilities and parameters from this, and you have to figure out how to account for this. And there's sort of two ways to do this. The first is you simulate a true neutrino energy spectrum, and then you input sort of a guess oscillation probability, and then you sort of smear that using some simulation software, and you compare your reconstructed neutrino energy spectrum with your data. So basically what you're doing there is you're doing a fit. You're inputting different oscillation probabilities and seeing what sort of guess best fits your data. The alternative, which would be kind of nice, is a little bit more direct. So what you try to do is you try to sort of unsmear your reconstructed neutrino energy spectrum, your data, into a true neutrino energy spectrum. From that, you would be able to directly conclude the oscillation probability from that. The problem with this second approach is that unsmearing process is not actually well defined. There are basically an infinite number of true neutrino energy spectra that you could get from your reconstructed spectrum. And in fact, what you have is a migration matrix between these two that's not invertible. So it's mathematically not well defined. So I'm just going to really briefly, well, maybe not super briefly, but briefly go through this first approach. This is sort of an interesting aside, but I think it kind of illustrates some of the difficulties that come up in running a neutrino experiment. So this is the case where you're guessing your oscillation probability, and then you're sort of generating a reconstructed neutrino energy spectrum and comparing with the data. So let's go through some of the new terms we have relative to our idealized experiment. So on the left-hand side, what we have is basically the number of events in the far detector divided by the number of events in the near detector. And you have a couple new terms here. The first is just a constant C that accounts for the difference in detector sizes. And then you also have your flux here. This is actually different for the far detector and the near detector. There are a couple reasons for this, but some include the solid angle that the two detectors take up in your beam, etc. So they're not exactly the same flux. Then you have your migration matrix. So this is the matrix I was referencing earlier. And this basically takes in your true neutrino energy and smears it out basically into a reconstructed neutrino energy spectrum. And then finally, we have sort of the most important part, which is your probability and then your cross sections. And these are both in an integral. So what you see in your experiment is the results of the integral, but what you're trying to extract here, this probability, is within the integral. So that's part of the issue. And then because the cross sections are here in your integrals, you can't just cancel them out. So it originally looked like we had a near-defart cancellation. Unfortunately, we're going to have to predict our cross sections, and that will become part of our uncertainty in our experiment. Okay, so we need to worry about cross-section modeling, and the question is, how well can we actually do this? So I have a couple illustrations. A really nice way to test these generators is to look at electron nucleus scattering data, because with electrons, you can actually measure the true energy. So this makes it a really nice way to test our generators. So this one is from a work by Yankowski and Friedland, and this just shows sort of the, in terms of energy transfer, your cross-section prediction and your data. So here we have two different energies and scattering angles. So the generator prediction is this black line, and then the data points are, of course, the data. And you can see for the first case, this peak is very far off, and actually also the tail. Basically, your generator disagrees with the data everywhere. This one, the peak, the basically quasi-elastic peak, does a little bit better, but again, in the tails out here, you disagree pretty strongly with the data. We can also look at E4nu. This is basically an experiment that was intended to do exactly this kind of analysis. Again, we have Genie here. This is the generator Genie. And they actually showed two different versions of Genie in the black line and the dotted line. So you can see even within one generator, there can be pretty significant disagreements depending on which version you choose. And again, these don't agree with the data. And then finally, what I think is one of the more interesting examinations, because it shows two different generators, is this work by Shirley that she hasn't quite published yet. But you can see here on the left, we have Genie, and here on the right, we have HEPEC. These are both relatively recent versions. And not only do they both disagree with the data, they also disagree with each other, which is a little bit concerning. And in fact, if you look at these sub-processes, the QE, the quasi-elastic peaks, are relatively similar. But you have, for example, quite a big difference in the prediction for resonance. This DIS line is basically the combination of your non-resonant pion 1 pi and 2 pi prediction. And you can see that all these sub-processes kind of tend to disagree with each other as well. And this is an issue that we'll come back to later. Okay, so we're not great at the moment at modeling neutrino-nucleus interactions, but the experiments are running. They're trying to do analyses. So how do they deal with this? The answer is they do near-detector tuning. So in this part, we're going to delve into what exactly near-detector tuning is and how it works. So the basic idea is that you're going to adjust your generator based on data at your near detector. That's more or less the original purpose of a near detector. So this is a schematic, and we'll get into the details more. But if you look at, for example, this is from NOVA, your Gini prediction that you have, that's the colored histograms here, you can compare with the data at the near detector and see that particularly at low visible hadronic energy, there's a pretty big discrepancy here between your simulation and your data. So what they're going to do is they're going to apply some tuning procedure where they modify their generator such that at the end, your simulation agrees pretty well with the near detector data. So I want to emphasize that inherent in this whole process is an assumption, which is that your near detector has a standard model and an unoscillated flux, because what you're trying to do is create a generator that result. For standard model oscillations only, this is actually a pretty good assumption because you're working at very short baselines. So if you think about NOVA, for example, the standard model physics that they're aiming to look at becomes relevant at a baseline of about 810 kilometers for their 2G EV beam. And the near detector is placed 1 kilometer from the beam source. So there's really no standard model oscillations yet at such a short baseline. So this is a good assumption if you have standard model physics, and that's it. Okay, so let's get into some more details of what NOVA actually does. We use NOVA because they actually publish their tuning procedure very thoroughly, which is lovely, so we can actually follow it and reproduce it. So again, what they're going to do is they're going to adjust the cross sections of their generator, which is Gini, to match the observed near detector spectrum. So before they actually get to that point, though, they implement a couple of changes to Gini based on other experimental results. These are not results that we're going to be delving into or changes that we're going to be delving into, but just to briefly summarize them. The first is that they adjust their quasi-elastic axial mass input value based on neutrino-deuteron scattering data. They also adjust the nuclear momentum distribution based on some results from Minerva. And then there's some reanalysis of bubble chamber data. And so they're going to reduce the non-resonant single pion production. So none of this is touching NOVA data yet. Then we get into the magnitude. So this is really what we're going to be focusing on here. So if you look at this histogram here, you have either the red or the dash. There's sort of two versions of Gini. After making those changes from the previous slide, there's still quite a bit of discrepancy between your simulation and your data. And you can see this for neutrino on the left and also for the anti-neutrino beam on the right. And so the assumption that's made from here is that the remaining discrepancy is due to MEC mismodeling. MEC is meson exchange current. It's pretty difficult to model. And so they assume that's where the remaining discrepancy is coming from. They also kind of assume that included in that is any process that maybe wasn't accounted for. So they're trying to be somewhat agnostic, but it's going to be adjusting the MEC contribution. And now what they're going to do is adjust it so that at the end you match the near detector data that you observed. So how does this work? This is kind of a wonky process to try to understand. But basically what they do is they take their simulation and they bin it in this 2D plane. So on the x-axis is the true Q, that's the momentum transfer from the neutrino to your hadronic system. And then on the y-axis you have the energy transfer, Q0. So this is about 200 bins. This gray region is just not kinematically allowed. And then what they do is they apply weights to each bin. So they re-weight the MEC cross-section in each bin by some value determined by a fit. They then migrate this into a simulated Q Rico and Q0 Rico plane. so that they can compare with the data. And then they compare with the actual data binned in that plane. And what they do is they do a fit where they adjust these weights applied to the true plane until they get their simulation to more or less match the data. So again, just to emphasize, for every single bin, there's 200 bins. You're just applying some weight that gets you the best fit to your cross-section for MEC. So this is not a physically inspired tuning, or it's not a physical tuning. It's not based on some reevaluation of the physics. It's just fitting, applying the weights, and then trying to
like done that
match
from
the
the
data.
very beginning, because like if I understand correctly, like
Yeah.
2 slides ago, like you're like adjusting parameters in a cross section. You should find exactly what you like the parameters.
Yeah. So these are separate adjustments that are based on other experiments that are probably a little bit more physically motivated.
But you could have just like, principally you could have just like bypassed all that, right? And it's like,
I think so,
done the thing at
yes.
the very end.
So in our analysis, we're actually not going to worry about these when we do our analysis. What we're really concentrating on is this MEC tune, because that's the part that actually adjusts your simulation to match the near detector data that you're seeing. Yeah. So it feels weird to do this as a theorist, because
I mean, you can do it. I mean, yeah, you
Yeah.
can do it. It does probably doesn't hurt anything, right? To do it, right? It's just,
We'll find
you have
out.
to keep, you have to keep track of it, I guess. Of course.
Yeah, so they do, there are many different ways to do a tune. And this is just Nova's procedure. In fact, Nova is actually updating their procedure as well. So now what they're going to do is basically do 2 Gaussians. So this color bar goes up to like 5. So down here, what you're doing is you're reweighting your MEC by 5. And up here, since you can't go negative, they basically go to 0. So they're trying to pull down the cross section. So they're trying to reduce the number of like degrees of freedom going on here, at least a little bit. But it's very experiment dependent what they actually do.
When you show the empirical MEC distribution,
Uh-huh.
it looks nice.
Yeah.
It looks like a Gaussian. It looks like we would hope.
Yeah.
I don't know. Is there any thought that goes into the NOVA procedure to keep it?
Keep it nice.
Yeah, I mean, because
Yeah.
if you do this arbitrarily, you can end up with a distribution that looks really unphysical.
Yeah, so I will say they do include the values of the weights in their fit. So they have what's the word I'm looking for? Penalty term for
Okay.
increasing the weight significantly. Because it would be kind of absurd to have like a region of like 100 times what you originally predicted. It would look kind of weird. But otherwise, I don't think, aside from the penalty terms, there's anything.
Do they try to keep the distribution of the weights continuous so that you're not like really weighting one bin up a lot and the neighboring bin down a lot?
Not that I'm aware of.
Okay.
Yeah, I think it's just penalty terms.
Okay.
Yeah, but you can kind of see, so for example, the tail, I don't know if you, there we go. I don't know if you can really see this, but the simulation does slightly over predict here on kind of this tail region and then under predict here. And that is more or less what you kind of see here. So for Q0 kind of correlates with visible hadronic energy. It's like the energy transfer. So visible hadronic energy should be correlated. And you can kind of see this region of larger weights here that kind of correlates to your low visible hadronic energy sort of under prediction. And then you have this region here that's kind of on that higher visible hadronic energy tail that's sort of trying to pull your simulation down. So it makes some sense when you see it. It's not complete chaos bin to bin. But as far as I'm aware, it's just the penalty terms and that's it. So that's the procedure. And when you do this, as we kind of saw earlier, what you get is a simulation that predicts the data pretty well. I'm not sure what's going on here with this last whole bin. I don't know why it's not able to fit, but otherwise it matches significantly better than it did before the MEC tuning, as you might expect, because you're basically tuning your simulation so that it matches this. So that's the procedure, and now we want to get into whether this impacts the physics searches. So that's really what the paper is about. Okay, so why do we care about this question? A lot of people have suggested looking for new physics in near detectors, and there are a couple of reasons for this. So the first, of course, is that it's very high intensity. if you're working with neutrinos, they're weakly interacting, you need high intensity in the first place. And at the same time, new physics typically has pretty low rates because it has to pass existing bounds, and those bounds tend to be pretty strong at this point. And so you typically need high intensity to look for them. So these near detectors are a really nice place to do that. They have higher statistics than, say, the far detector because they're placed closer to the beam source. You also have a weakly interacting background because they're neutrinos, that's your beam background. So you have a weakly interacting background. And then the final point, which is very nice, is that these experiments are already built or are already being built. So you can take an existing experiment and try to extract a lot more physics out of it than maybe was originally intended. Okay, so what kinds of new physics searches have been proposed? I'm just listing 4 here. So the first is, for example, EV scale sterile neutrinos, and we'll get into that again a little bit more in a minute. You could also have neutrino-philic scalars, which might be portals to dark matter, for example. People have proposed looking for tritium production and near detectors, which is another pretty low rate process. And then you might have, for example, light dark matter beams that get produced in your neutrino beam as well. So these are just 4 examples. And I just want to emphasize again, if you're doing these searches, you have to worry about cross-section mismodeling. And so you basically have 2 choices. The first is not to perform a tune at all, and just kind of hope that your mismodeling doesn't skew your interpretation of new physics when you're doing your search. The second is to perform the tune, and because you're basically doing this sort of free fit to your near detector data, you can risk tuning away the new physics because you're adjusting your sort of quote standard model generator to match exactly what you see at the near detector. So in order to examine the impacts of this, we're looking at 2 example models. So the first, oh, you have a question, Kevin?
Yeah, could you go back to the schematic you drew of the tuning procedure?
Yeah.
So you said, or one more. Yeah. You said that they have roughly 200 bins in this Q versus Q naught space.
Yeah.
Do they fit to more than just this visible hadronic energy spectrum? Because it looks like you have way more degrees of freedom in your tuning procedure than data points.
Yeah. So what they're doing is they're fitting in this plane.
Oh, okay.
So they do bin their near detector data in this 2D plane.
Okay.
And then they fit their sort of reconstructed spectrum for the simulation to that data.
Got it.
Yeah. Okay. So we'll focus on 2 example models. The first is the EV scale sterile neutrino, which is basically going to be a modification of the overall event rate that you're going to see. And the second is going to be neutrino-philic scalars, which is more or less a low rate additional new physics signal on top of your background. So what we're asking is, how much does the interplay between your near detector tuning and any cross-section mismodeling interfere with your new physics search? Okay, so here's our basic process. So first what we're going to do is we're going to generate 2 standard model simulations using neutrino generators. So for our analysis, we'll use either G or Neuro. Then we're going to inject the new physics signature into one of those simulations to create sort of a mock data set. And then we have 2 options as outlined. The first is just to examine this new physics signature without doing any tuning. And the second is to perform the Nova Mech part of the tune of our model simulation to our mock data. And then after we do that, we'll examine what the new physics signature looks like with tuning. And then of course, we'll compare the 2 and see whether tuning washes out our new physics signature and whether we're actually sensitive to new physics. Okay, so the first model is a light sterile neutrino. So this could be obviously like 3 entire talks, but the short version is that you have short baseline anomalies as some accelerator experiments and also some reactor experiments that point towards a light sterile neutrino of a mass about 1 eV. Basically, what you have is sort of an excess of electron neutrinos in a muon neutrino beam at short baselines. These baselines are much shorter than you would expect from standard model oscillations. And so what that means is that you need, hypothetically, a new sterile neutrino that has a much larger mass splitting so that you actually get oscillations at that baseline. So of course, this light sterile neutrino would mix with standard model neutrino flavors in order to make that happen. And actually, Fermilab has a whole program, the short baseline neutrino program, that's examining this possibility of sterile neutrinos. again, in short baselines, hence the name. So what is there we go. What does the signature actually look like? So you can basically write down the effect of a sterile neutrino at short baselines in sort of an effective two flavor oscillation setup that we were looking at previously. So here what we'll be focusing on is survival probability of muon neutrinos, because the nova beam is muon neutrinos, and we're looking at the near detector. So muon neutrino survival is going to have pretty good statistics and be a nice search. So if you write down the probability, you're modifying sort of your standard model expectation of about 1 with your effective mixing angle, that's what the state of mu is, and then your oscillation term. And again, this depends on the mass squared splitting of your new eigenstate with your standard model eigenstates. And then you have your L over E. So given that your mass squared splitting is about 1 eV, or at least that's what it appears to be based on your anomalies, your oscillations actually become relevant at a ratio of L over E about 1 when you write them in terms of kilometers and GeV. So this is interesting because that's more or less where near detectors tend to live. So for example, for nova, what we have here is the nova near detector is placed about 1 kilometer from the beam source. And the spectrum for nova peaks around 2 GeV. So we would expect that for mass squared splittings on the order of 1 to 5, etc., you would actually expect to see an oscillatory signal here. So here what we've plotted in blue is just an example muon survival probability for a given mass squared splitting of 5 eV squared, just our choice, and then a mixing of 0.2, just to make it a very visible signal. And so you can see this sort of wiggle signature, and that's exactly what we're going to be looking at. Okay, so to start out with, what we're going to do is we're going to use the same generator for the mock data and for our sort of standard model simulation. The reason for this is that it gives us sort of a conceptual understanding of what the tune is actually doing. So it's not yet quite a realistic analysis. We'll get to that in a minute. But this at least shows us if you were to have a perfect model of nature, does the tuning wash out your new physics? So again, what we're looking for basically is this wiggle. If you take the ratio of your data to your standard model, you would expect to see this oscillatory signature like the one we just saw in the previous slide. So if you look at the signature, in the blue, we have our mock data divided by your standard model. So that's just your basic untuned expectation, and you see the wiggles as you expect. If you do the tuning, and then you look at the result of the mock data divided by the tuned standard model, you can see that the wiggles are actually very much still there, but they've been shifted vertically. So the shape is actually still remaining, which is kind of interesting. So now we can look at the case where we take different generators. So this is probably a more realistic examination because we expect that we have some mismodeling between our generator and nature. And so using 2 different generators gives us a sense of how that mismodeling might affect our search. So what we're going to do is we're using G again for our mock data, and now we're using Neuro for our model. And again, the relevant curves are going to be this blue curve, which is your data divided by standard model. And then you have your red curve, which is your data divided by the tuned standard model. In this case, the oscillations are not quite so clean because you have 2 different generators. But again, we can see that performing the tune doesn't wash out these oscillations. The signature more or less survives. But there's a bit of a caveat here, which is that if you look at the difference between the 2 generators unmodified, so this is like GE standard model and Neuro standard model, there's actually sort of a wiggly signature that kind of looks a little bit like the wiggles that we see from our sterile neutrino. So there's a question about whether the generator mismatch on its own is going to bias our interpretation of these results. So before we get into that bias, let's just ask ourselves, why can't we tune away the signature in the first place? Because of course we're adjusting our generator to exactly match our near detector data. Why can't we tune away these oscillations? The reason is basically that neutrino energy isn't actually directly correlated with the tuned parameters. And this makes some sense because experiments are looking at signatures of neutrino energy. So they want to choose parameters here that aren't necessarily directly correlated with neutrino energy. So here, just to illustrate that, what we have is a plot of the distribution of events for a range of the neutrino energy between 0.5 and 0.6 GeV. And then on the right here, what we have is basically the same thing, but just a different energy range, so 2.9 to 3 GeV. And you can see that there's pretty significant overlap between these two, even with very different energy choices. And because the oscillation depends on neutrino energy, as long as there's significant overlap at different neutrino energies, you won't expect there to be a shape in this plane that you can actually tune away. Okay, so now we're going to actually do a sensitivity analysis. So what we'll do is, again, we're going to use two different generators so that we can understand the effect of mismodeling on top of tuning. And we're going to do a direct fit to near detector and far detector rates, which I believe is more or less the analysis that, for example, Minos has done. And we'll do a simultaneous fit and tune when we're doing tuning. So the idea being that hypothetically, your tune could account for standard model differences, and then your new physics signature is going to go on top of that, and combined, they might tell you your best fit, which hopefully will be the true parameters. We do just a chi-squared fit. We use a covariance matrix with these systematic uncertainties. So we just assume there's a 20% uncertainty in the overall normalization, and then 2% each for near-defart spectral correlated uncertainties, and then a 2% bin-to-bin uncorrelated uncertainty. So this is what we get when we do this. So this is kind of the main result for sterile neutrinos. So we have three different curves here that we're looking at. The first, this gray region, is actually done using Gini for both generator model and data. And the basic idea behind this curve is that it tells you sort of the true 2 sigma sensitivity on region. So if you had a perfect model of nature, this is the sensitivity that you would expect to get. And here in the center is our true input parameters. So we're using a mass squared splitting of 5 EV squared, and we're using a mixing of 0.1. Then we have our two sort of new row curves. So the first one in blue is the region that you get if you do this fit without any tuning. And you can see that it's actually pretty skewed relative to your true region. It tends to prefer larger mixings, which might be intuitively reasonable given that you had sort of that pre-existing wiggle already between the two generators. And so that really just makes the signal look stronger, basically. And in fact, at 2 sigma, it excludes the true input parameters. And then if you look at the tuned case, I would say it does better than the untuned curve, but it's again a little bit skewed, particularly in mass squared splitting. At least it includes the true input parameters at 2 sigma. So this is one example, but we wanted to do this with another example, mass squared splitting, because it was kind of curious that we just chose a splitting of 5 EV squared, and the generator mismatch kind of looked like that exact signature. So we wanted to try this with a different set of input parameters. So here what we chose is a splitting of 2 EV squared. And this is an interesting, also very different case. So for the untuned region, it actually sort of looks like there's no new physics. If you looked at this region and you saw this, you would probably conclude that there's no new physics. And again, it excludes your input parameters at 2 sigma. Then you have your tuned region, which last time did a little bit better than the untuned region, but it also excludes your true input parameters at 2 sigma. And another thing to point out here, which is rather unfortunate, is that there's not a consistent bias. If you look at this region here versus this region here, it's skewed in different directions. This also tends to prefer larger mixings, whereas this one doesn't. So there's not necessarily consistent bias where I can say, okay, my tuning procedure affects my sort of inferred region, but I can account for it in a consistent way. That's not the case here. There we go. Okay, so what's the basic takeaway here for sterile neutrinos? The basic idea is that you seem to have some biased sensitivity to a sterile neutrino signal. So the signature itself is not correlated with your tune plane, so you don't tune it away. And you do have some sensitivity to the existence of new physics. But your tuned and untuned regions don't actually perfectly correspond with your true sensitivity region. And in fact, they sometimes exclude your true input parameters at 2 sigma in our case. And because the skew is different depending on the input physics parameters, you can't simply consistently account for the skew and therefore perform your analysis for whatever input parameters you choose. So that's the sterile neutrino case. Now let's move on to a different type of signature. So this is a Mononutrino model. The basic idea is that it could be a neutrinophilic dark matter portal, and it's also related to lepton number violation. So it's a model where you could imagine that there's a connection between dark matter and neutrino masses, for example. So the basic idea is that you have your operator here, you have L alpha with the Higgs, L beta with the Higgs, and then you have your new scalar phi. This is a neutral scalar. When you have electroweak symmetry breaking, what you end up with is an effective interaction between nu alpha, nu beta, and your scalar phi. So this is this lambda here is just your v squared divided by this new physics scale squared. And this is the model we're going to be working with. So what you have is a new neutral scalar that interacts with neutrinos. That's the key part here. So what does this look like in our neutrino experiment? Well, basically, your neutral scalar is just going to skip, and so it appears to be missing energy. So the basic setup is that you have your neutrino or your antineutrino, in our case, coming in and radiating off of phi. Then it interacts via charged current, and out comes what appears to be sort of a wrong sign lepton. So given your neutrino or antineutrino beam, you have a lepton coming out that appears to be the wrong sign for your beam. This would be very nice if we had charge identification, for example, in NOVA, but unfortunately we don't. You just see the muon coming out, but you don't know the sign, so you can't use that to cut down on your background. And in fact, if you look at your sort of uncut backgrounds compared to your new physics signal, there's orders of magnitude difference here. So if you want to be sensitive to this, you're going to have to apply some experimental cuts. So here, just in blue, what we have is G, and then in the black points, what we have is neuro. And order of magnitude, they agree. There's a slight disagreement in sort of where your peak is in missing energy. But in any case, whichever one you use, you're going to have to apply some cuts to see your new physics. So that brings up a question, which is how do you actually approach tuning and cuts? Because there are two obvious options. The first is to tune before applying the cuts. And the second is to tune after applying cuts. So at least to my brain, tuning before applying cuts initially seems like the obvious choice. But as we'll see, it doesn't work super well. And we'll look at the case for both of these and see how it affects our new physics signal. So neutrons are not actually detectable for NOVA because they're neutral particles. So in order to have a visible final state, what we're doing is we're going to focus on the antineutrino beam. And what we're going to do is cut on one visible proton, no pions, and no visible neutrons. So for NOVA, the kinematic threshold is more or less 100 MeV. So that's what we mean by visible proton or visible neutron. It just means that they're above 100 MeV kinetic energy. And what we're investigating here is just how do cuts affect the impact of the tune on your new physics search. Okay. So again, just like the sterile neutrino, we're going to start out with using the same generator for your data and your model. In this case, we're using neuro. And this is looking at the first option where we're tuning before we apply the cut. So here, the really key part to look at for this plot is this lower panel. In red, we have the difference between the data and the standard model divided by the standard model. And in black, we have the same thing, but for the tuned standard model. And interestingly, the tune appears to do basically nothing if you tune before cutting. And the basic reason for this is that you have, say, order 10 to the 6 events before you cut, and you're tuning to some variation that's many orders of magnitude smaller than that background. And so the values of your actual weights are going to be very small deviations from 1. If you then cut and you reduce the number of standard model events and you apply those same tune weights, they have very little effect. That variation is very small. So this is an interesting result where if you tune before you cut, it doesn't have any real impact on your new physics search. Then you can consider the alternative, which is to tune after cutting, and we'll see why you care about this in a minute. And in this case, you might expect that it would completely wash away the signal, but in fact, it doesn't completely wash out the signal. It does affect the strength, but it doesn't. You don't lose your signal entirely. And this seems pretty surprising at first. So we tried to figure out why this is the case. And the basic reason, again, is the distribution in the tune plane. So in this case, what we have is we have our cut standard model on the left and then our mononeutrino events on the right. And this is just sort of like a heat map of where these events tend to be in the tune plane. And what we see is that for the cut standard model, they tend to be pretty localized to a certain region, whereas the mononeutrino events are spread pretty evenly across the plane. And in fact, you have a decent number of mononeutrino events where there's really no standard model to tune to. So what you have is new physics events that your standard model can't actually adjust to because there's just not really a standard model background there to adjust. And so what happens is your new physics signal actually can survive this tuning procedure. So this seems very nice. And we can try a sensitivity analysis to see how much this tune actually does skew our sensitivity. So again, we're doing a chi-squared fit, this time just to near detector events. And in order to create a covariance matrix for our missing energy, we're just using the following systematics for PT bins. So again, an overall normalization of 20%, and then a bin to bin uncorrelated of 5%. So these are just values that we hope are reasonable and can give us a sense of what a sensitivity analysis might end up looking like for NOVA. So again, this isn't perfect. Hypothetically, what you would probably want to do is take a covariance matrix in EDU and modify it to work for PT. But here we just want to get a sense of the impact of tuning and mismodeling, not exactly reproduce NOVA's analysis. So if we do this, this is what we get. So again, in the gray, we have sort of our quote true region. We have the same generators. We're not doing any tuning here. So if you have a perfect model of nature and you don't do any tuning, that's your sensitivity. And then if you do the tuning after cuts, that's this red region. You can see it shifts a little bit what your best fit region is, but you're not excluding at 2 sigma your input parameters. So we would consider this a reasonable success. So this all seems very nice and promising, but there's a huge issue lurking, which is that our generators react to these cuts that we're applying very differently. So if we can just look at the standard model to standard model comparison here, again, G is in blue and neuro is in black. And if you apply the cuts, this is what you get. So there's a lot going on in this plot. Sorry, I'll try to explain it. So the blue here is the post-cut GE prediction, and the black dots here are the post-cut neuro prediction. And there's a very large discrepancy between these two. And in fact, this discrepancy is much larger than the new physics signal that you're looking for. So this is concerning because what it tells us is that our mismodeling is actually, or the discrepancy coming from potential mismodeling is actually much larger than the new physics signal that we're trying to search for. So we can ask whether tuning saves us. And that's what we have these 2 dashed lines here. So the first one, the gray dashed line, is what you get if you tune Gini to neuro before you apply these cuts. So if you had sort of a physical tune that got it absolutely right, you would hope that if you tune before cutting, you'd still have them match up. But in this case, that does not happen. There's still a very large discrepancy between this tuned Gini generator and your V-row. On the other hand, you can tune after cutting, and this does a little bit better. But there's still a pretty large discrepancy here. This is a log scale relative to your new physics signal. And you also find that you're kind of overshooting here on the tail. So any new physics that you add is just going to make that discrepancy worse in that tail. So why is this happening? Basically because we're cutting to like corners of parameter space. And what that means is that discrepancies can just become exacerbated when you're cutting to these sort of corners of parameter space. And generators also predict different cross sections for the different processes and also different final states, and we're cutting on our final states. And so you end up with very different results. If you recall, our 2 generators, what we're doing is we're sort of cutting down to particular processes. And if you recall, these generators actually disagree pretty strongly about what those individual processes are contributing. So that's a real issue. Another issue that might come up is that we're tuning mech, right? And when you apply cuts, you can adjust the amount of mech relative to the rest of your processes. And so if you, for example, have mismodeling in something other than mech, your tune will fail once you cut. So this is perhaps disheartening, and we can ask ourselves, okay, there's a big discrepancy between generators. It appears that mismodeling is much larger, for example, than our new physics signal. Maybe it doesn't really make sense to do a sensitivity analysis, but we did one anyway, just to see what happens. So here, this is more or less similar to our sterile neutrino case. So we have in gray here our true region where we're using the same generator. In blue, we have our untuned 2 sigma best fit region. And then in red, which you can barely even see on these plots, is actually our 5 sigma tuned region. And we had to do 5 sigma just to make it visible. So on the left, what we have here is we haven't input any new physics, and we're just looking at what your sort of exclusion regions would be. And it looks pretty promising at first because this untuned region successfully concludes that there's no new physics. It's slightly shifted relative to the true region, but you can once again say there's no new physics here. And that seems great. The problem is if you put some new physics and try to search for it with different generators. So this is our true region that we saw earlier. And once again, your untuned region concludes that there's no new physics. So in fact, your generator mismatch is just completely dominating over your new physics. And this tuned region down here, again, very, very strongly excludes your true input parameters. So what's happening here? So basically, we're not tuning away the new physics, which seems great because of their distributions in the tune plane. But tuning doesn't save us either. It doesn't account for the differences between generators. And again, this difference between generators is kind of a proxy for the difference between our generators and nature. And tuning doesn't save us from that. And the reason basically is that we're cutting through corner parameter space where those disagreements between your 2 generators can just become worse. They can become exacerbated. And unfortunately, that mismatch dominates over your low rate new physics and you lose sensitivity. Okay, so that brings me to my conclusion. So hopefully I've convinced you that cross sections are a very important part of these neutrino accelerator experiments, and that this near detector tuning that they perform plays a major role in how we interpret these spectra in terms of new physics or standard model oscillation parameters that we're hoping to measure. So we need to make sure we understand the kinds of impacts it has. So if we look at a signal that has a modification of overall event rates, we find that that kind of signature can survive the tune, but you'll end up with biases in your best fit sensitivity regions that aren't also resolved by tuning. Then, of course, for low rate physics, like our mononeutrino signal, where you have to apply some cuts, we find that there's a significant generator mismatch, and that just dominates over your new physics and you lose sensitivity. So really what we need here is better theory predictions and or better experimental solutions to this issue so that we can actually unlock the full power of neutrino experiments. That's it. Thanks very much.
Okay, so questions for
To your sterile like parameter measurement plots.
Yeah, the sensitivity plots.
Yeah. Yeah, that's okay. So especially on the left panel, what this says to me is that if you have some model of nature that is G, and if you analyze it using G, you get some measurement region. But if you analyze your data, even if you do it right, taking the tuning into account, you can get a completely biased result.
Yeah.
Right. And that scares me when we're thinking about new physics searches, but wouldn't the same be true then of NOVA with standard 3 flavor physics? What makes this special with standard physics? Yeah.
Yeah, that's a good question. That's actually something we kind of want to look into next.
Okay.
Yeah, we might look at, for example, like the Minos sterile analysis or the NOVA standard model analyses. Those are 2 things we're interested in next.
Yeah, I'd be curious if this is unique to BSM searches or if you'd see similar problems at 2 sigma with extraction of standard oscillation.
Yeah, definitely.
That's the follow-up. Like, do you know why T2 and G they differ drastically?
Which one? Oh, for the electron scattering data?
Yeah.
This is gonna take a minute to
Because,
go upstairs. I am honestly not sure why they differ quite so drastically. Yeah, it looks like, for example, the resonance is really driving this discrepancy here. But I'm not certain why the two disagree so strongly.
Then this three flavor, like even standard model analysis could go wrong because it.
Yeah. Yeah, I think we definitely want to do that analysis next. I'd also be interested in doing this kind of analysis that we've done here with, well, I don't really need to go into it, but doing another region with, for example, Kibu as your third generator, just to see sort of what range of regions you would get for different generators.
Oscar, if you ever have the chance to go to a conference focused on neutrino generators, I highly encourage you to go.
No,
because-
those are so discouraging. I would stop thinking
No,
of BSM.
No, it's great because they have some of the strongest personalities. And so they will argue why their generator is
The
given
best.
from God and correct, and the other generator is not to be listened to.
So, another question I have. So, just to get some information about your success and defeat based on this analysis. So, do you have any example where you have truly tuned away the
Yeah, so
based on this?
we haven't looked at a case that does completely tune away the new physics, but I think anything where you have a shape, let me just go back to the tuning procedure. Yeah, anything where you have a distinct shape in this tune plane, I think you would be at a real risk of tuning away. So for like the sterile neutrinos, basically what you end up with is just like a flat overall shift in the number of events. And yeah, I mean, the mononeutrino would have been washed away if there was full coverage from your cut standard model. But we don't have an example here where you completely wash it away. I would say that that's something probably people could keep in mind though, when they're thinking about their models. I will say for NOVA, they actually don't do a tuning procedure when they're doing their BSM searches. As far as I know, that's basically just a sterile neutrino analysis. I don't know of any other analyses they're doing. And I think it's partly because they were concerned about this. But I think for me, then I would be very concerned about this mismodeling issue. If you're not doing the tune, then you're just accepting there's a significant discrepancy between your generator and your measure. So
this is a question from a low energy nuclear experimentalist. So this may go horribly wrong. Is it possible to use this tuning procedure to try to tell you what's going wrong with the generators that already exist? Because there's parameters and there's things in here. I'm just wondering, is it like a black box? You put in something, you get a response matrix, you kind of go, okay, we've got the right answer now. Or is it possible to use this to say, well, actually, these things are where there seem to be systematic problems in the existing data?
yeah, so I think so I talked to a grad student who's on the NOVA tune at a conference, and she said she's interested in looking at the impacts of different processes on the final result. And I think that would be a really nice way to understand where these discrepancies are really coming from. Because right now, of course, we're just tossing everything into MEC basically in this case. And it's quite possible that MEC is not the only issue. So I think breaking it down into processes is very nice. And actually, some theorists have been talking about making some adjustments to your different processes and then saying, end result, how much does that change your inferred parameters? And I think that would also be a nice way to get some stronger understandings of the uncertainties that you're getting from this.
I actually have a couple of questions. The first question is related to our process question. So I understand. Okay, so you just the tune. So whatever the generators, GE, GU, or the neural with the NOVA data, and then that you can study whatever neutrino sector physics using the tune generators.
Mm-hmm.
But then, so given the fact that the Jibu and the Genie, they predict the neutrino scattering cross section very different. So then, can we use these tuned generators for other neutrino experiments?
Yeah, so I think probably not. It's pretty experiment dependent. So every experiment has their own tune procedure that they do,
I see.
and they can be very different. So I think most experimentalists, I should ask them, but I think they would feel pretty uncomfortable having another experiment directly using their tuned generator. In fact, I have, yeah, I'm just gonna go.
So there's like a response matrix or something like especially when it's different. Yeah.
So I guess
Yeah, so here,
to
I find this kind of interesting. This is again courtesy of Shirley. This is a plot of your mech. So here's your Nova tune in orange. And then here's, for example, your T2K tune in purple, kind of blocked a little bit by the legend, but you can see it. They're very, very different, which is also kind of concerning.
Can that be chalked up to differences in materials in the detector, or is this much bigger than a difference than you'd expect?
I think that's a much bigger difference than you would expect, and I think it comes down to the specific tuning procedure that you're doing, because Nova is accounting for basically the entirety of their discrepancy with Mac, and so they're pushing it up quite a bit.
So okay, so then the message is that every single experiment they should tune the generators with their own data, just they're choosing some control regions, and then the study.
But maybe that goes back to this question. Maybe if multiple experiments compare what their tunes say, if they're pushing in the same direction or a different direction, in showing that a generator is wrong,
Well,
maybe we can learn something from that, right?
so actually, in my personal opinion, I guess so as far as I remember, each of the generators they take a different resonance production models and etc. So I mean, some of them are first the principle inspired, but sort of the empirical, but then they're working in the different the regimes. So probably they're very the different. I mean, I think that this is very similar to the PTIA or the Horby tuning, with the collider data. But then even if PTIA and Horby take a different head radiation models, conceptually different, but surprisingly the end result is converging to each other. So even if they tune the data, with some LHC or that data. But then they can safely extrapolate their tuning to other colliders. Well, there's still there's some debate whether they can they use the PTIA or the Horby tuning with the left data for the LHC physics. But there's still both generators converging to each other. Yeah. So, but I guess in this case the model builders, I mean the resonance, the production model builders, they should get together and then make like a consensus or something like that. Yeah. But then they say, okay, so my model is
it's very fun.
I got Rocco. Now the second question is, so I guess your basic assumption is that at least at the production level, like imagine production level, so you don't have the significant uncertainties up to a normalization.
Yeah.
So okay, so the production part doesn't have any issue.
So you mean like the flux of the beam, more or less?
Yeah, right. The shape. Well, I guess the uncertainties are coming from like the scattering level and even the flux level, right? So
yeah. So there's, I mean, Nova tunes their flux and their cross sections separately.
Okay.
So there's like a separate flux uncertainty, and then this part is just tuning.
So they understand the production level uncertainties. And
they should, yes. I think they use some Minerva results. I'm honestly not an expert on the flux tube,
I see.
but they use like some simulations, and given the current and the focusing horn, et cetera, they have some
I see.
level of uncertainty that they seem to be reasonably confident in.
Yeah, so the reason why I'm asking this question is, so Peter and Horvik, they tune their parameters using the lab data. Because, well, you might say, well, the LHC, you could use, the LHS data, but then LHS comes with another uncertainties, right? So PDF uncertainties, even at the production level, so you don't know what's going on, right? So two non-perturbative QCD, so they involve production and the heterogeneous level. But the lab data, so you fully understand the production level. So you get rid of the uncertainty in the production level. So you end up with just heterogeneous uncertainties, and then you just fit the data into their models, right? But here, I guess even at the production level, right? So
Don't they know what they use the same?
Yeah, they're on the new.
right, same NUMI, but then the production level, we don't fully understand the pi-ion production, k-ion production, and the PP collision. That's the problem, right? So
do you think, but it's kind of overall normalization?
yes, that's why. So I guess there seems like a basic assumption is that shade is fully known.
Yeah.
The only unknown is just lower normalization. I'm not. Is it really true?
Well, they might also use neutrino electron scattering. They might also use neutrino electron scattering data
I think they do.
to constrain that because that cross section is so well known.
That's right.
But they can use that process, albeit at a lower rate.
Like from others.
Or from theirs or from Minerva.
I
So
think
then, how
they
do you
do
predict
use
the neutrino, electron neutrino flux?
Not the electron neutrinos. Neutrino mu-mu's scattering off electrons in a material.
Right.
That process is much.
But you should know the flux of the other nu-mu.
You use that process to measure flux.
Yeah, because you have a well-known cross-section and you can observe the rate and for the.
But that's that you have two unknowns and that you have one equation, and then somehow you.
No, you know that cross section.
So the
The
cross.
mu electron cross
Okay,
section.
electron flux. Yeah. Okay, I see.
Yeah, so someone pointed out that it would be good for us to sort of grab the actual systematic variance matrix, because that would have, if there's any sort of shape uncertainties, that would have that as well. And that would be interesting to try out. Yeah.
Okay. Other questions for her? If not, let's think,